Modern AI agents operate under a strict execution paradox. To perform complex tasks, they require Turing-complete capabilities, but current communication methods force a choice between high token costs and significant security risks. This comparison illustrates the problem. On the left, a standard JSON tool schema is secure but token-heavy, lacking native logic like loops. On the right, the same intent expressed in Inthon requires 40% less data for the same action. The alternative is generating raw Python code. While this provides the necessary logic, passing unvetted Python scripts directly into a runtime environment exposes the host's operating system to arbitrary execution side effects. Inthon resolves this by acting as a Python-hosted programming layer designed specifically to execute AI intent within a restricted environment. By representing agent actions as structured code, Inthon secures the host architecture while keeping the context window footprint minimal. Inthon achieves this by treating LLM output as a formal computation graph to be compiled, rather than a loose string of text to be interpreted. The engine processes commands through 5 stages: lexing and parsing, AST generation, semantic analysis, policy guard, and sandbox execution. To see how this prevents errors, we'll track a hallucination-prone command, an unauthorized web search, through this exact pipeline. The baseline benefit is clear. In a standard research task, the token footprint drops from 90 JSON tokens to just 52 in Inthon. By routing logic through a strict compiler, the engine ensures that hallucinations are caught before they ever interact with the host machine. Stage 1 utilizes a specialized EBNF grammar and a LARC LAALR parser. This replaces standard string parsing with a formal system that recognizes only valid Inthon syntax. This grammar allows the model to express complex instructions with minimal tokens. A human approval gate requiring 70 JSON tokens is compressed into just 19 tokens here. In Stage 2, the lexer converts the raw token stream into an abstract syntax tree. This immutable data structure organizes the agent's intent into a hierarchy of operations. If the LLM hallucinates incorrect syntax, the tree fractures statically, blocking execution before it begins. Contrast this with standard scripting, where a syntax error might only be triggered after a destructive runtime process has already started. The AST acts as the engine's first physical barrier, converting unpredictable text into a structured format that must satisfy the grammar's rules before moving forward. Once the syntax is verified, the engine enters Stage 3, semantic analysis, where it validates the context and meaning of the code notes. The engine performs 3 sequential passes. It checks the scope, infers variable types, and analyzes the program's static execution capabilities. By building a symbol table and a scope chain, the analyzer identifies undefined references, preventing logic errors and memory leaks before execution. This stage addresses a key technical challenge. Agents need access to libraries like pandas and NumPy, but standard Python imports are too permissive for a secure environment. Inthon solves this through PyBridge, a 2-level security gateway for the Python ecosystem. Level 1 is the module allow list. Dangerous system-level modules like OS, sys, and subprocess are strictly blocked. This enforces engine invariant number 4. Safe modules pass, but hazardous operations are neutralized before the import resolution even begins. Modules that pass the allow list are wrapped in an Inthon Py object proxy. This object intercepts every attribute request and filters it against the active execution policy. This architecture allows agents to leverage advanced data science tools while keeping the host operating system isolated from the execution environment. In Stage 4, the AST is lowered into a flat, JSON serializable intermediate representation, or IR. The IR represents the program as a dependency graph, where every tool call is an explicit node. The policy engine inspects this graph. If an agent attempts unauthorized network access, that specific tool node is blocked. This stage handles resource metering, enforcing hard limits on execution time and total tool invocations. If a tool's cost per call combined with the agent's planned iterations exceeds the budget, even by a fraction of a cent, the system triggers a sandbox violation. Because this happens at the graph level, invalid logic stops before instructions reach the processor. Bounding capabilities in the IR ensures that resource limits are enforced by the engine's logic rather than the model's instructions. Finally, the verified graph reaches the sandbox execution stage, running in a strictly isolated environment. Developers choose between a tree-walking interpreter for debugging or the Inthon VM stack machine for speed. Critical actions, like database writes or financial transactions, are protected by the human approval gateway. These gates are synchronous. Execution halts entirely until a human grants permission, ensuring no critical action is ever bypassed or skipped. As the code runs, the sandbox emits a cryptographic JSON tracelog. Every expression evaluated and every tool used is recorded deterministically, creating a complete audit trail of the agent's behavior. This replayable log provides the transparency required for enterprise deployments, allowing engineers to verify exactly how and why a decision was made. To understand the impact of this pipeline, we have to evaluate it against the typical failure modes of autonomous agents. These benchmarks compare Inthon against raw Python. While Python is slightly faster in raw execution, it lacks mechanisms to handle agent-specific failures. Under stress, Inthon identifies and escapes infinite loops in 600 milliseconds, providing safety guarantees standard environments cannot match. The minor latency of the compiler is a necessary trade-off for eliminating hallucination-driven errors and ensuring 100% execution safety. By enforcing a strict syntax, Inthon ensures that security is a property of the code itself, rather than a suggestion in a prompt. It provides a formal framework that treats agent intent as a structured computation. Ultimately, this allows for the creation of workflows that are cheaper to generate and safe to execute at machine speed.